But okay, my name is Lionel. I'm up here and I'm going to talk about evolving high availability at Braintree. The word evolving is the most important part of the talk. Okay, so who am I? What even is Lionel Barrow? I'm a software engineer at a company called Braintree. I've been here for a bit over 3 years now. Unlike I'm sure a lot of you, I'm mostly an application developer. I can already see you grabbing the fresh, ripe Maryland tomatoes, cocking them, ready to throw. But I have a little bit of operational experience, but not too much. But I have had sort of a finger in each of the different pies that I'll be discussing, and I think that hopefully you'll get a good perspective. So what even is a Braintree? Braintree is an online payment processor. We make software that allows other businesses to accept payments both online and on mobile devices. I will always think of Braintree as this sort of small company that I joined like about a year after college, and like it was 20 developers, maybe 60 people on the whole team as a whole. We just moved into a nice office in Chicago, and that was about it. But we are getting pretty big now. We were acquired by PayPal in 2013, and we kind of exploded pretty fast. So we recently announced to the world that we're doing roughly $50 billion a year in annualized authorized payment volume. Now, to break that down, that sort of means that if day and night didn't exist, there was no cyclic day and night cycle in payment volume, and there was no weekly cycle or monthly cycle or indeed seasonal cycle, that meant that roughly our software is handling $95,000 a minute in other people's money. And I say other people's money because it's critical to our ethos that like we are not making this money. It'd be great if we were making $95,000 a minute. Let me tell you, I would feel pretty good about that. But we don't. Instead, it's merchants who are trusting us with their business are the ones who are making this money. And they're trusting us with their business in a very literal sense. If we are down, they're unable to accept payments. So for us, I take this number and beat it over the head of new hires with it to put the fear of God into them, not because I'm mean, but because it's very important that we sort of respect this. We're a silent partner for our customers. And even though many of you have never heard of us, you've all interacted with our software when making purchases on Uber or GitHub or many other different online merchants. And those people trust us. It's not just big technology companies either. We also have small mom-and-pop e-commerce merchants, people who don't really know very much about software development. They also trust us to keep our site operational so that they can accept payments. So downtime is really bad for us. So let me back up a little bit and talk about why am I here. In about 2011, 2012, it started to become pretty obvious that Braintree was going to be a very successful business. To anyone who was paying attention. We were growing really fast, and we were starting to do pretty creative things in order to keep our primary APIs operational, even while we did maintenance and stuff like that. We put in place, for example, a custom HTTP proxy, which I'll be talking about at length, called the Broxy, the Braintree proxy. There was clearly a ball was dropped on the floor with that, but nonetheless, the Broxy, it was a very interesting piece of software, and we started to do a lot of other different creative stuff for our high availability story. And so what do software developers do when they feel like they've accomplished an interesting project? Well, they go and give conference talks about it. So our fearless leader, Drew, was like, this Broxy thing we built is going to make a great conference talk. And so he went and did one. And then Paul was like, good idea, Drew. I'll come up with some more practices, and I'll throw them into the pot, and I'll do some conference talks as well. And Paul really went on tour. He talked at Strangeloop, he talked at Velocity, he talked at Surge in 2013. He somehow finagled a trip to Australia to talk about this in Australia, which was good for him. So we kind of went on tour with this stuff. Finally, Tony and a different Paul, Finzi, also did a talk here at Surge, not so much about the Broxy, but about other practices we have. And I think looking back on it, that was an era of sort of explosive creativity and sort of the way we were trying to solve these problems. And we were very happy to talk about them with other developers and sort of, have fun doing that. But that was all 2 or 3 years ago. And I think a reasonable question for people to ask is, so guys, how did this actually go? Like, what actually happened? Maybe we should have a talk that's sort of looking back and saying, now that we had all this stuff about high availability at Braintree, how did it actually go? And so that's sort of what I'm trying to do here. So I'm going to walk through what we did, the crazy sort of systems that we invented and put in place. I'm going to talk about each of the, 3 of them Not in too much depth, because a lot of this stuff has already been covered, indeed, at Surge in previous years. But I'll give a little brief overview. We'll talk about, OK, we scaled up. And then I'll say, what came next? What is the current state of the system in 2015? OK. So to do this, I need to prime you on what our world looks like. Fundamentally, this is what things are this is our situation. You've got consumers and merchants. Merchants being a sort of broadly defined entity that means someone who wants to process payments online. They're sending us requests all the time. And most of these requests we can't actually handle ourselves. So when Twitter gets an API request, get tweet of /ID foo, they can answer all the they can sort of figure out, if the question being asked by this API request is, what's this tweet? They can answer that question from within their own data center. But we don't. We can't answer the question, can this card be charged $5 or $7 for GitHub Premium? We have to go talk to someone else to answer that question. And the people that we talk to are basically banks. Or they're not quite banks. They're sort of bank-like entities that we generally refer to as processors. So you could look at this arrangement and say, well, why doesn't GitHub or Uber or whoever just talk to the processors themselves? It's a reasonable question, and certain very large businesses do indeed do this. But critically, OK, I was told that it's not a good idea to come to Surge and start slinging mud around and just shitting on other companies. But I'm going to put it to everyone here that this proposition, let me know if this is out of line. In my experience, financial institutions don't make great APIs. It's out there. It's out there. I can't take it back. It's been my experience that that's the reality. OK, so there's that. You would have to integrate against what, let's be frank, are a series of terrible APIs. You might also want to accept more than one payment method. Is certainly a good reason. So you'd have to build an integration against American Express and an integration against PayPal and whatever. Or Braintree can multiplex this stuff for you. And almost more importantly, we are a level 1 PCI DSS compliant entity. We can handle raw credit card data, and most businesses don't want to do that. That's a huge amount of burden. So there's pretty good reasons why you would actually want to do this. But this is our world. So these are our merchants, just to give you a sense of who's using this. I think that the thing to note is that you have both highly sophisticated technology companies such as Uber, who we recently saw a whole talk about how sophisticated they are, and Airbnb and GitHub, but also people like Casper. Casper sells mattresses. It's an e-commerce company. So you have a wide range of different types of people using the API. But from our perspective, this means that we live in a world that is very write-heavy, in which many of the questions that people are asking us in the API we can't answer within our own data center. We have to go somewhere else to answer these questions, possibly over the ocean. Who knows? Also, as I sort of mentioned, to us, every single request matters quite a lot. If you're looking at cat pictures on Reddit or wherever, it's not that big of a deal if a single request is dropped. Now, obviously, if it's a percentage type thing, yeah, it's not good. But for us, every single request that we get basically directly makes someone money, not in the sense that in some way there's ad revenue being generated. It's like, no, they're about to make $7 for their premium subscription to GitHub. And if we drop them on the floor, they've lost money. We've lost money too, but they've lost money. And of course, the app is evolving really fast. These are the constraints that our operations teams are faced with. So what do we do? I found that whenever you have a complex problem or series of problems that human beings are attacking, you never have a response that is pure practice, right? There's always a theory or a philosophy or an idea of what you're trying to do in an abstract sense that guides what your day-to-day tactical decisions. And this is our theory. Our theory is that the way we want to achieve operational excellence is with small pieces, simple pieces, that are open source whenever possible. Critically, that these pieces must be understandable on their own, very, very understandable. And we will create an intelligent, robust system by composing these pieces together, by composing components, which sounds really dumb when you say it out loud. And we'll emphasize, when we're designing our system performance under stress. It is so easy, anyone can design a system that works well when things are working well. Just, have some queues and one thing talks to another thing, and it's fine, it doesn't matter. What's important is how your system behaves when things are not going well. when your queue lengths are long, when request times are taking forever. There's some firestorm in the cables that connect, the United States to Europe, and all of a sudden all of your European requests are taking forever. Like what happens? Does the system fail does the system fail at all? If it does fail, does it fail in an intelligent way, or does it sort of go berserk and shoot all its neighbors? This is what actually matters. So here are the tools we're going to use. We're going to talk about the Broxy, which I will kind of go into immediately after this slide. We'll talk about our load balancing stack, which we use Linux IPVS, and then we use 2 custom pieces of software that we wrote called Big Brother and Litmus Paper. We'll talk about Pacemaker and how we use that. Pacemaker, again, a thing that we did not write ourselves, but we use. And Rails and Postgres, which I'm not going to really elaborate on. I think that everyone kind of knows what that feels like, but is nonetheless part of this story. This is what the application level stuff looks like. It's Rails and Postgres. So OK, what's the Broxy? Well, this might be like the sort of thing that is like, what? About this talk? The Broxy is a web service it's an evented web service written in Python using the Tornado library. It takes requests from Apache that's our sort of exterior, serializes them into Redis, and then something downstream is listening to this Redis queue, pulls the entire request body, everything from like HTTP, blah, 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 get thing, pulls that off into itself. It's Rails, spoiler alert, processes them, puts the response back into Redis, Broxy slurps the serialized response back up, and sends it on its way. So is anyone already sort of thinking like, what? Yeah, seriously, sure. I actually have talked about this with people, and they literally did not believe that this would work. Someone was like, that system wouldn't work. Guys, if you took an Uber anytime in the last 5 years, you've used this system, so you have to believe it worked. Or else you're like, I don't know, the people who deny evolution, but they take azithromycin, not penicillin. OK, but yeah, so this is a little bit crazy, right? But why would you even do this? Well, so here's the architecture I described. You have a load balancer, which is your exterior thing. It's talking to Apache, Broxy, Redis, and then Rails pulls from Redis, right? The red arrow going the opposite direction means that Rails is pulling from Redis. Everything else is pushing. So what's cool here is that what happens if Rails goes down? We get rid of the Railses, and basically just end up with a fat Redis, right? One of the constraints when you have the fat Redis is that it adjusts the boxes and positions in your slides, but we can deal with that. So Redis gets really fat. From the perspective of the clients talking to the load balancers, this just looks like things are slow, right? Like, OK, I haven't gotten a response, what's going on? Apache is keeping the connection alive. So what do you do then? Well, you bring the Rails back up, and it will drain from the queue. It's a first in, first out queue. So you process these like requests that were first got to you first, and then it just looks like things were slow. But in reality, your API was totally down. Nothing was happening. All traffic had stopped. OK, so what we finally did here was that we, the critical thing is that we're able to pull the request out. We've introduced a pull step into HTTP. So that's the critical thing this gets us. And this is actually, turns out, really useful. The links here, when I put the slides online, these will be real links. But we can pause traffic totally, all traffic hitting our Edge API, for whatever amount of time we feel is reasonable. We typically have picked 30 seconds, which is slow, but it's not catastrophic, right? This allows us to do zero downtime database migrations, even if they require exclusive locks on the tables in question or something like that. We can do zero downtime database failovers. In fact, using a zero downtime database failover this way, we're able to move our primary data center. This is back in 2011 or something like that, 2012. I don't know. We moved our main data center across town without any resulting downtime. Indeed, no one probably noticed anything happened, except for maybe the API was slightly slow for a couple seconds. So this is pretty useful, right? Like, how many people really want to have like a stop the world button on their operations? OK, I was expecting more hands, but yeah. You can do some cool stuff if you have this. OK, so that's the Broxy. Let's put that aside. We'll talk about the other stuff that we did. Load balancing. We wrote our own load balancing and health monitoring systems from scratch. So I don't want to go too much into this. One, because Tony and Finzi did a really good job of this at Surge in 2012. Also, Pilot is going to be talking a lot about this tomorrow. Michael Pilot, who's our production engineering lead. It's going to be a really good talk. It's a sponsored talk, but he's basically, I think, going to tell some like crazy stories about you do what thing. It's going to be good. But let's talk about what we actually do. So requests are routed around using Linux IPVS, which is a kernel module. Like I said, I am an application developer. I reserve the right to, if I get too many questions about IPVS, I will delegate them to the table of Braintree people sitting right there. You are sitting there, and I see you, and you can't escape. But what we have is, OK, so you're going to route things around using IPVS. IPVS has weights. You can sort of say, like, OK, I want to weight things so that this request goes there or whatever. This percentage of requests. And so Big Brother is a Ruby program that we wrote that runs on the load balancing server itself. It constantly pings its dependencies, the things that it's going to route requests to, and says, how healthy are you, how healthy are you, how healthy are you, how healthy are you? And it knows how to take those requests, understand their responses, figure out an intelligent routing algorithm, and then to manipulate the IPVS weights such that requests are routed well. Litmus paper, on the other hand, is the thing that's reporting back the health. It's another Ruby daemon. It runs on the box. It just provides a DSL where you can say, OK, my health, which is measured from 0 to 100, is defined by some input of my CPU load, my memory, my disk I/O, and maybe some application-specific health checks that I'm going to write. And this allows the application developer to write these health checks pretty easily. So we sort of see how this works, right? Like, are you healthy, are you healthy, are you healthy? Litmus paper responds. And the critical thing is that all of these tools are very, very simple on their own. We wrote like 2 of them. They're not that much lines. It's like a couple hundred lines of Ruby. Like it's very easy to reason about how Litmus paper and Big Brother will behave. By composing them together with this kernel module, we're able to create a system that, even though it's composed of simple pieces, nonetheless is actually quite intelligent and quite robust. So Big Brother, for example, has a reasonable amount of intelligence in its weight-adjusting algorithms. For example, it knows to do things like, if a new node comes into the system and it's 100% healthy, I don't want to send every single request to it. That will just take it down. So it has a stateful component where it kind of knows about time. But nonetheless, it's like its behavior is totally isolated. Its view of the world only depends on these health checks. So it's very easy to reason about what it will do. Litmus paper, as I think you can tell, is also quite easy to reason about what it will do. So I think that this is sort of like the classic case of the philosophy that I've advocated working. OK. Finally, let's talk about Pacemaker. Pacemaker is hard to explain what it is. Who here knows what Pacemaker is? Just immediately. OK, I see some hands. OK, cool. So people are like a little bit familiar with it. Pacemaker describes itself as a scalable, high availability cluster resource manager, which is a lot of words. Words like scalable and resource are kind of bloodless. They kind of could mean anything. But fundamentally, what this allows you to do is you just say, these things are a resource that must be up. This thing is acting as the primary provider of this resource at this point in time. And Pacemaker, if you notice that there's something wrong with this thing that's providing this resource, here's how you transition from this thing being the primary to this other thing being the primary. The 2 canonical uses of this thing is sort of clustering load balancers so that you have a highly available load balancer cluster, and database failover. So let's talk a little bit more in depth about how that works. So suppose you have some load balancers that are routing requests to Rails, and you basically just need to say, Load01 is servicing this request. It's doing its regular, Big Brother, Litmus paper dance, and things are going well. But then all of a sudden, someone kicks the cable, Load01 goes down hard. Pacemaker is running on each of these machines, and it knows to say, oh, Load01 is down. I need to fail over to one of these 2 other nodes, but not both, because if both or neither of them become the new master, you have a bad problem. So Pacemaker, it uses a consensus algorithm similar to Raft or Paxos or whatever, or Zoogrub or whatever the Zookeeper one is. And it figures this stuff out. It does this for you. But it's a general purpose program. So you can sort of define ways of saying Pacemaker fail, this is what it means to be healthy, this is what it means to be failover. OK. So this is load balancing. What does database looks like? Well, database stuff is a little bit more complicated. We have a large number of sharded Postgres clusters. For us, a Postgres cluster means that you have a primary that's accepting reads and writes. You have a synchronous secondary that's accepting writes synchronously. In Postgres terminology, that means that a write is not considered to be committed until it is committed into the secondary as well, which means that it's not possible for you to have data loss in the event of a failover. Instead, you can only have aborted transactions at the moment when things happen. And then you have an asynchronous standby that's sort of just like, it's getting writes eventually. So the array of shards, the primaries and secondaries are managed by Pacemaker, and Pacemaker essentially knows how to promote the primary, how to, in the event of the primary failing, how to promote the synchronous standby into the new primary. Now, automated database failover has a kind of nasty reputation. There have been some big, high-profile problems that have resulted from it doing the wrong thing. In particular, if your system can fail from one primary to the secondary and then back to the original primary, things can go wrong pretty badly. So this happened to GitHub in, I think, 2012. This happened to them on some of their big databases, and it resulted in some inconsistencies, like some data loss and stuff like that. We sort of keep things simple. You can only fail in one direction. OK, and so that's how we use Pacemaker. So those are our tools. That's what the situation was. What happened? What changed? Well, I don't want to really be tooting our own horn here, but basically we got a lot bigger. So in September of 2013, we were doing 10 billion in annualized authorized payment volume. It's important to get this terminology correct, actually, turns out, because we are owned by PayPal, which is a public company. I would point out that these numbers come from blog posts that were published by our CEO. So if anyone wants to get mad at me for publishing them again, too bad. But yes, as you can tell, we roughly doubled, a little bit over doubled every year for the last 3 years. So what changed? That's really the crux of this talk. Like, which of these systems that I've described actually stood the test of time? OK, so let's talk about the Broxy. We ripped it out. It died. We ripped it out, we replaced it with HA proxy. Now, why would we do this? Aside from it was maybe a crazy idea to begin with, but it did actually work. The Broxy continued to work for years while we doubled several times. It just, in the end, wasn't quite what we wanted. So it's not that crazy. Why did we rip it out? It got a lot more complicated. It became less useful at the same time as it was getting more complicated. And even as it was getting less useful, we were still exposed to the bugs that it generated. So how did it get more complicated? Well, the Broxy in a lot of ways was already always complicated. It has to fundamentally keep state on requests that are in flight. So we are really good software developers, so we don't make this mistake. But you can imagine a world where we do things incorrectly, where, for example, you have some health check on the Broxy that is measuring the length of the queue, and you have to sort of like, you have to traverse the queue to measure the length. This would create the dynamic I was talking about where, in a failure scenario, things actually get worse and it fails in incorrect ways. Now, we're smarter than that, a little bit. So we saw that problem coming, and we actually have good use of data structures and so forth. But I think you'll notice that when you denormalize information around a system like this, you actually end up with like a more complicated piece of software, right? You have to remember to increment a counter or decrement a counter or things of that nature. That's just sort of one example. So it got more complicated, though, because we wanted to start using it for other things. We wanted to start using it for rate limiting. Now, someone in this room is probably freaking out at the idea that their payment processor would rate limit them, right? Like, hey, I'm just having a good day. I'm selling a lot of cookies, and you're rate limiting me? Come on. We have to do this. We have to do this because it's important that no single one of our merchants is able to saturate our entire API and sort of take over it. That, from the perspective of everyone else in the system, is an outage. And it's important to realize that this won't just happen because someone's having a good day. It's going to happen because some developer somewhere at maybe a relatively small place will ship some code that just sort of like while one pings Braintree for something. And we can't let that take us down from the perspective of everyone else who's using us. So we do indeed have some quality of service protection. You also have the potential for malicious clients or indeed, just people having a really good day. But so as we started to add this rate limiting code to the Broxy is in the correct position to do this. You would want to do rate limiting after Apache or around the same place where you terminate SSL, but you don't want to do it by the time it hits Rails. That's too late. You've already used resources. The Broxy is well situated to do this, but adding the rate limiting code to this piece of software made it start to feel very complex and increasingly brittle. Everyone knows the feeling when it's like the developers don't want to go onto that code base because it's like they're afraid basically that they'll have one line of code wrong, it'll take down production, and like that'll be terrible. It started to have that smell. But like I said, we're good developers, and like we can overcome a code base that has gotten out of hand, right? Like we can refactor it, change it, make it better. We can improve him. We have the technology. But we didn't. And the reason why we didn't was because at the same time as it was getting worse, it was getting less useful fundamentally. Rails it has this fantastic property that the bigger the Rails app is, the longer it will take to boot up. By 2013, 2014, it was starting to take 10 to 15 seconds for our main application to start. Someone here, there was a bunch of Rails jokes earlier, which I endorse all of. So if you're going to have a 30-second window in which you can pause stuff and do interesting things, and you actually only can use 15 seconds of it because your app is going to take that long to start up after you've done the interesting things, like you're starting to really get to the point where it's not really buying you that much, right? Moreover, some situations in which we would want to use the pausing functionality, we no longer really had to. So at one point, we had enough Rails processes running that we started to need a connection pooling mechanism for our Postgres clusters, so we use PG Bouncer for that. PG Bouncer allows us to do a failover between databases and take much less of a hit than we would if we were not using anything. So imagine, if we wanted to do a database failover, you can pause traffic at the API level and wait for connections to drain and then just fail over. That will work. You can also sort of try to do a just fail over, really fast. And PG Bouncer helps you do this. It's not as smooth. You do still have this thing where you'll lose transactions that are in flight. So Rails will probably result in some 500s, but not that many. Is that correct? You don't lose transactions? Okay, even better. I thought there were problems. Okay. Well, even more awesome. Even less use cases for the Broxy, right? Also, sort of in terms of absolute scale, just the longer you're running this thing, the more pressure is building on the system, the more throughput you're doing overall, even more pressure is building on the system. I think it just starts to look very, very risky. So I don't actually know the date of the last time we actually used the with Broxy sort of pausing feature. It was, I think, late 2012, early 2013. No one wrote it down because I don't think we actually thought it would be the last one. It was sort of just like we did it and just never actually ended up doing it again. But we stopped using the primary feature of this system. Okay. But even that wouldn't be that bad, except that it also kept causing problems. Even though we weren't using the actual, pause the traffic everywhere feature, we still were exposed to the surface area from having all these components that we otherwise would not have had. Who here happens to know that in, I don't even know the versions, the version 1.3.2, that's a made-up number of the Python Redis client, what maximum object size you can pass through the, No one just happens to, that's not a documented number to you or something like that? Yeah, so we ran into this. We ran into this because an internal user was downloading a report, a very large report, and it was the report's contents, which were going to come out through the Broxy, were too big to go through the Redis client. I believe it was the Redis client, yeah. So what would happen then is the user clicks, give me this report. The request goes in through Apache, passes through the Broxy, the request is serialized through Redis, it's slurped up by a Rails process, the Rails process does all the work to generate the report and process it, and then it sticks it back into Redis, and the Broxy is like, okay, cool, I've gotten my response back. I will then pick it up and hand it back to Apache, except when it goes to pick it up, it's like the proverbial, leans down and the Broxy's arm falls off, right? It's this poisonous request that causes the Broxy app itself to crash when it attempts to service the response. So what would you do if you were using a web service and an operation that normally did not time out? This is, by the way, clearly a timeout from the perspective of Apache, right? Because it never gets the response. And so if you're using this application and you say, oh, usually I can get this report, no problem, click, times out, what's the next thing you're going to do? a couple more clicks, right? Yeah, give it a go. So that was bad. It was, I would say, a service degradation, not really a true outage. But it's like, but I think this is like a representative example of the types of things that we ran into, right? We had this thing that was working most of the time, but had this surface area for bugs to sort of rear their ugly heads out of. A surface area that would be both smaller and probably like more covered if we're using a more robust tool, which we ended up switching to. There was other things. The push-push-pull workflow was non-standard and confusing to people. I don't really think I need to dwell on that too much, but imagine, for example, what order do you shut things down in if you want to take random parts of the system offline for maintenance, if you're doing like a rolling restart type maintenance thing, right? Another point would be that because the Rails processes are not listening on HTTP, it's actually difficult to do health checks on them that are independent of this entire stack. So like how do you, for example, ping the Rails app and say, how healthy are you directly? You sort of have to go through the whole Broxy stack because the Rails process is actually listening on the Redis port for input. That's like where it's going. It's sort of, all this stuff kind of added up to be quite annoying. And finally, of course, HA proxy in 2012 was not the HA proxy of 2015. This was, far from an obvious choice at the time. In fact, HA proxy started in like 2011 or something, I think. Anyways. Okay, so yeah, we ripped out the Broxy. So what changed with the load balancing stack, right? Okay, we've got the Broxy, load balancing stack, then we're gonna talk about Pacemaker. Not much, boom. This is the best thing you can ever say about software, right? We've been using it forever, and we have not touched it in like years. That's not quite true. We added like active-active or something like that recently. But fundamentally, the IPVS, Big Brother, litmus paper stack that I described to you continues to be what we use to this day, even though the number of services that we're handling, the volume of requests, and so forth has grown dramatically. It just has not been a problem. We've done minor bug fixes, feature additions, and so forth, but the fundamental architecture is still in place. So what can you say? Nailed it. Boom. So what changed with Pacemaker? Pacemaker, I think, is in a little bit of a middle ground between you ripped it out entirely and you basically did nothing to it. With Pacemaker, we ran into some really big problems. So CoroSync's interface. CoroSync is the thing that knows how to manipulate Postgres for Pacemaker. It's sort of the middleware between them. Remember, Pacemaker is a very general purpose piece of software. It doesn't really know how to do the stuff itself. Sorry. The particular version of the particular version of the particular version of things that we were using, I believe these are all fixed later on. But the particular version of CoroSync's interface with Pacemaker we found had pathological performance problems on very simple operations as the size of the cluster under management grew. So this is sort of like, I think it was of the form of constantly checking health. Like it was sort of like, are you up, are you up, are you up? And CoroSync's code essentially assumed that this would be a free operation when it was, in fact, was linear with the number of nodes in the Pacemaker management. So this made our database operations increasingly perilous, but we were able to fix it by rearranging our use of Pacemaker. So you recall that we had basically this, where the big box is what's under management as a single Pacemaker cluster. You can fix this by doing this, where instead of one big Pacemaker cluster for your database stuff, you just have n, where n is the number of Postgres clusters that are being managed. So that sounds really simple. It was not. This was a big project, in particular because anytime you're doing this sort of stuff, first of all, just discovering that it was this particular performance problem was a lot of work, I'm sure. I didn't do it. But also the work to rearrange the Pacemaker clusters in this way was very heroic. I was supposed to mention this, but I don't have my speaker notes up here. But the work to rip the Broxy out also sounds really simple, but it was not. Fundamentally, it's this sort of 2 steps forward, 1 step back character of replacing a component of infrastructure where you make a change, see what's happening, find some more problems, have to go back a couple environments, and keep on going. It required quite a lot of dedicated work for a production engineering team. In particular, Jesse Hathaway and Andrew Hayworth. So Andrew basically joined Braintree and then was told, okay, you're going to be on the Rip Out the Broxy project, and that was it, But he stepped up to it, so that's awesome. And then Brian Cosgrove and Caitlin Perry did a really good job about this on the Pacemaker side. And Cosgrove gave a detailed talk about this particular topic at Postgres Open last week, if you're interested. I don't know if he actually went too deep into the problems we had, but whatever. Okay, so to conclude, I guess this went pretty fast. I think we got the theory right. Our theory was that a small set of understandable components on their own can add up to an intelligent, robust system. I think we got this right. This remains our approach to tackling problems to this day. One of the critiques you can make about the Broxy was, especially by the end of its life, it was no longer a small, understandable component. It was the thing that did the middleware, which was not a position we want to be in. I think that it is normal and healthy for an organization to go through highly experimental phases and then follow them up with phases where you evaluate what went wrong, what didn't, and you take the stuff that didn't wrong out to pasture. That's totally good, actually. Being afraid to try new things in this way can be just as damaging as sticking with off-the-shelf products or NIH stuff that you wrote yourself. As an aside, don't be afraid to try stuff. Like Braintree is not an HTTP proxy company. You don't have to be, the people, well, okay, I say that, but turns out there's also some other HTTP proxies that we've made. As software engineers, the best thing about our jobs, in my opinion, is that we get to create the world that we then live in. So you get to go into your system, create the abstractions, create the fundamental architecture, set things up how you want them to be, and then you're going to live in that world. That's how things work. That's how things work when you do a service-oriented architecture. It's how you work when you lay out your data modeling and so forth. It's also how it works when you set up your basic tools. So just because you're not an XYZ company doesn't mean that you can't make XYZ basic piece of equipment. I think that, that's basically it. I think that overall, high availability is a very difficult project, but with a small, determined team, you can pull it off. Especially now that you've learned all this stuff about what not to do. So here's some links to the previous high availability talks that I was trying to position this talk as an evolution of, and that's it. There's no way for me to end the slide. There you go. Cool, I'll take questions. Yeah? Nothing? No questions? Whose idea was it to do this crazy thing? I don't know. It's probably Drew. We can blame Drew. Yeah.
So you've got this Rails app that takes 15 seconds to start. It sounds to me like that's not a small, simple. Is there a way to replace that with something else?
So the question is, it sounds like we have this Rails app that is big enough that it takes 15 seconds to start. That doesn't sound like a small, simple, and composable component, or I would add understandable. That's completely accurate. We've actually had, for several periods of time, we've had dedicated teams breaking, called like the decomp team, that's gonna go break off piece of this thing and transition us to a more modern service-oriented architecture. It turns out that Rails is indeed very hard to refactor in dramatic ways, so that has been slow going. But yes, we're aware. I gave a talk last week at Windy City Rails in which I talked about this exact problem, sort of the pain of living with a long-lived monolithic Rails app. And one of the charts I had was a chart of our commit history over time. So it started in like 2008 or something like that when the gateway was initialized, and you see sort of like a familiar type of exponential growth of commits. And it makes it look like we're really dumb, right? Because it's like, oh, monorails, that was really cool in 2006 when Twitter was doing it, but it's not a good thing to do in 2015. It turns out that if you graph commits into all other services that we started and you stack them up, they're starting to outweigh the number of commits that go into the gateway as a whole. So we are kind of transitioning, I think, away from this architecture, but it's slow. More questions? Yeah.
When the Broxy would crash, because of the Python Redis bug, would you lose like all the requests that were to you, or just the one that failed?
Okay, so the question is if the Broxy crashed for the Python Redis client reason that I gave, which I was intended to be, that's an example that is representative of other problems, but did indeed happen. Would you lose everything, or would you really just lose the request that like timed out in between the time it took to restart it or something like that? I don't actually know that off the top of my head. The Broxy did have to keep track of requests that it was servicing. I think that you would lose everything that was in the queue, but I'm not sure. Yeah? Okay. Pilot's give me a thumbs up. In the back.
It sounds like you're using Redis as a message queue. If you look
So the question was, you're using Redis as a message queue. Why didn't you use a real message queue? At one level, I was not there for this decision. I think I was very much not around. But I think that Redis does have some nice properties here. It's easier to introspect like the queue itself in Redis if you're using something like Redis than it would be for Rabbit, I believe. I also think that in terms of like where the Redis was, it was just sort of, honestly, I'm not sure that there's a whole lot of great reasons. I think that RabbitMQ is like a little bit harder to introspect like what it's doing as it's running than Redis is, especially because it's like, we literally just had like a Redis, like, I think it was a list or a queue structure, which you can go in and is like very simple. And this data is intended to be ephemeral, right? So it's not really like you're worried about like, oh, you should use Kafka because then you would never lose the request. The request is going to be over in 60 seconds, like, period. Yeah. Does that answer your question a little bit? Okay, cool. More questions? No saboteur questions from the Braintree audience? Good. All right, cool. Thanks, everyone. I guess I was a lot faster when I was going through this live than I was at practice, but oh well. Thanks a lot.